Welcome to this puzzle session. Here is the problem. 5 lattice points are chosen on the infinite square grid. So this is the infinite square grid. It extends infinitely in all directions. And here so far I've only drawn 4 points. But we are given 5 points on an infinite square grid. So every point of this grid, every little dot that we see here is called a lattice point, right? So 5 lattice points are chosen. Now we want to prove that 2 of these 5 points have the property that their midpoint is also a lattice point. So for example, these two, if we pick and take the midpoint, it is somewhere here and hence not a lattice point. It's not on the square grid, it is somewhere outside. Same for these two, same for these two. So you will find that these 4 points do not have this property. You cannot find 2 of them whose midpoint is also a lattice point. But as soon as you add one more point to these 4, inevitably you can find 2 of those which have this property. The midpoint will be a lattice point. So let's say I add the 5th one somewhere, wherever, let's say here. This is my 5th one. Then, well, the midpoint of this is probably here, so this doesn't work. But the midpoint of this is that guy. So this, these 2 points have this property. And you can experiment and be convinced that this is indeed true. So we will prove this. Of course, you're encouraged to pause the video and think about a solution yourself before jumping to what I'm going to describe. All right. So first, let us discuss some preliminaries about the setting. So suppose we have 2 lattice points. So I'm using the coordinate notation. This denotes the x coordinate and this denotes the y coordinate. These are of course both integers. So suppose we have 2 lattice points, then what is their midpoint? Their midpoint is just something that we learn in high school coordinate geometry. So that is their midpoint, and therefore the midpoint of the given 2 lattice points is again a lattice point if and only if both are integers, because lattice points are precisely those points whose both coordinates are integers. So this is again a lattice point if and only if x1 plus x2 and y1 plus y2 are both even. Okay, very simple. And this can be reformulated as saying the following. The midpoint of the given 2 points is a lattice point if and only if x1 and x2 have the same parity and y1 and y2 have the same parity. So what do we mean by parity? Parity of a integer is the remainder it leaves when divided by 2. So the parity of 3 is 1, the parity of 4 is 0, the parity of 5 is 1, and the parity of 6 is 0. So x1 and x2, when they have the same parity, their sum will be even. Otherwise, their sum will be odd. So this statement and this statement are basically equivalent. Okay, so with that, we move on. We define something called the type of a lattice point. Suppose we are given a lattice point x comma y. We say that x comma y has type EE if x is even and y is even. So E stands for even. We say it has type EO if x is even and y is odd. O stands for odd. It has type OE if x is odd and y is even. and OO if X is odd, Y is odd. So there are only 4 types. Every lattice point has one of these 4 types. And now, just reformulating or rewriting what we have discussed, we have 2 lattice points, x1, y1 and x2, y2. Then their midpoint is also a lattice point if and only if they have the same type. So this is what we need to realize to finally finish the proof. So here is the proof now with that fact in hand. We will use the pigeonhole principle. A primer on it is available in the playlist named Kickstart. And perhaps I will not forget to put a link in the top right corner of the screen. So we have these 4 types. Think of them as cages, and every one of the 5 lattice points that we are given as pigeons. So we have 5 pigeons and 4 cages. Therefore, 2 of these pigeons must share a cage, and hence the 2 pigeons which share a cage, their midpoint will be a lattice point. And that's it. So with that, I want to end this. Thank you for listening, and I'll see you next time.